Hello and welcome to the class. So today we are going to discuss and I'm going to start the unit number 2, uh, discrete Fourier transform. Okay. So in the discrete Fourier transform, you can see that discrete time Fourier transform, okay, DTFT of a sequence is a continuous function of omega. Okay, it is a continuous function of omega. Omega, you all know that omega is equals to simply 2 pi f. Omega is equals to 2 pi f. Okay, and repeats with period 2 pi and repeats with period 2 pi. Okay, so in practice we usually want to obtain the Fourier components using digital computation. Okay, and can only evaluate them for a discrete set of frequencies. We are going to only evaluate them for a discrete set of frequencies. Okay, so a discrete Fourier transform DFT provides a means for achieving this. We basically need this. Okay, evaluate them for the discrete set of frequencies. Okay, so the discrete Fourier transform is itself a sequence. It is simply a sequence and it corresponds roughly to samples. There are the samples. Okay, so discrete Fourier transform provides a means for achieving this. As I have told you, the discrete Fourier transform is itself a sequence. Okay, it is a sequence and it corresponds roughly to samples. There are the samples which are equally spaced in frequency. Okay, some samples are given which are equally spaced in a frequency of a Fourier transform of the signal. There is the signal. Okay, so let us see this. The discrete Fourier transform of a uh, length capital N. The length is given, length capital N, signal xn, where n is equals to 0 1 up to n minus 1. Okay, this is simply given by the discrete Fourier transform is given by x k for a signal n. Okay, just remember this. For a signal n, summation of n is equals to 0 to n minus 1 x n e to the power minus j 2 pi by capital N into k n. Okay, so this is simple. The discrete Fourier transform is given by. All right, so this is the analysis equation. Its synthesis equation we can write down like this, that is x n. Okay, this must be equals to what? 1 upon capital N summation, where k is equals to 0 to n minus 1, 0 to n minus 1 x k, okay, e to the power j into 2 pi by n, 2 pi by capital N into kn. Okay, so this is simply the synthesis equation of the above equation. Okay, now simply when dealing with the discrete Fourier transform, it is very common to define the complex quantity. Okay, so the complex quantity here should be Wn, which is equals to e to the power minus j 2 pi by n. Okay, so this is the complex quantity we are using in the discrete Fourier transform. Now from this you can see that with this notation the discrete Fourier transform analysis synthesis pair becomes the analysis and the synthesis equation we have already written on the last slide, where now just changing this e to the power minus j into 2 pi by n with wn. Okay, we are just uh, changing this. So the above equation given in the last slides will become xk. This should be equals to summation of n is equals to 0 to capital N minus 1. Okay, xn is simply given over there. Xn is there. That must be changed to wn. Okay, we have changed this to wn. We are writing this to the power kn. Okay, it was already given over there. And its synthesis equation can be written as x n, this should be equals to 1 upon n summation of k is equals to 0 to n minus 1, okay, n minus 1 x k x k, okay. Now wn, w capital N minus k n. So the above equations can be write down can be written like this. All right, you can also write down very easily. Now an important property of discrete Fourier transform is that it is cyclic, okay, because the period is given over there with a period capital N, both in the discrete time and discrete frequency domain. Okay, just to remember, both in discrete time and discrete frequency domain we have the time period of capital N over there. Okay, now for any integer small r, what we can write down this, uh, we can write down this as uh, x xk was given over there, so we are just writing for any integer r as r capital N. This is this r, okay. This should be equals to what? This should become summation as equals to 0 to capital N minus 1, okay, xn, the signal given over there, wn was there, but the power is changed to, instead of k we will write down k plus small r into n, okay, small r into capital N into n, okay. We have just changed that equation. Now if you are going to open this, if you are going to open this, we can write down this equation as all this also, n is equals to 0 to n minus 1 x, n is a signal given over there, w capital N to the power kn, okay. Just opening this, w n to the power, we can write in this kn, and we can write down as r n, okay, like this also we can write down. So this must be, this must become n is equals to 0 to capital N minus 1, xn was already there, okay. We are just writing this as w n to the power kn, okay. This will become 1 over here, and now this equation finally will become as xk, okay. So this is the, you can understand this, we have the it is a cyclic we have discrete Fourier transform, it is a cyclic with the time period of capital N, okay. Now similarly its synthesis equation we can also write down it. It is easy to show that x n plus rn, okay, we are taking the period over of n over here, is equals to xn. We can also write the signal like this, implying the periodicity of the synthesis equation. So synthesis equation we can also write down just as we have uh, written earlier this equation. So this is important, even though the discrete Fourier transform only depends on samples in the interval of 0 to n minus 1. So it is implicitly assumed that the signal repeats with period n in both the time and the frequency domain, okay. So here the signal is repeating itself, it is repeating itself. So as I can tell you this, that we have written wn, we can write down this as w, just to make it clear, wn, you must be in doubt that how it become 1, okay. We can write down this as this must be equals to what, minus j to the power 2 pi by capital N into n, okay. It should become what, e to the power minus j into 2 pi, because n should get cancelled out, and it should become equals to 1. All right, so this is how we have solved this equation. So now I think it must be clear to you, okay. Now to this end, it is sometimes useful to define the periodic extension, okay, the periodic extension of the signal xn, okay. uh, this is sorry to be uh, signal xn to be, how we can write it as x, and just we have taken this is as a bar, we just called it, okay, n. Okay, how, what is this? This is simply, we can denote is like this, that this is n mod capital N. Okay, and we can rewrite this as uh, x is outside the bracket, where n capital N. Okay, here n mod capital N, and this one's in bracket small n, then capital N, the suffix, are taken to be mean, mean and modulo capital N. What is this? Which has the value of remainder, which is simply have the value of uh, here it is being written, taken as n modulo capital N. Okay, which has the value of remainder after n small n is divided by capital N. Okay, alternatively in another language, we can write down this as, if n is written in the form of like this, that small n is equals to k capital N plus L. This is L. Okay, this is L. For L is equals to from 0 to capital N, then what we can write in, we can write this as, this is simply n mod capital N, this is equals to L. Okay, so if there is a signal like this, this is 0. Okay, so the pulse are giving like this one, this one. Okay, this is a discrete signal. Okay, discrete signal up to n. This is what, this is a simple xn. Okay, but x bar n is given like this for a period. This is similar. Okay, but it is repeating, it is getting repeat. Okay, this was like this, and the signal on the left of this is also like this. From 0 to capital N. Okay, this is for signal xn. So similarly the periodic extension for xk, okay, for the discrete Fourier transform of xn, okay, this can also be written as x bar of k, this should be equals to capital X, okay, k mod n, which is equals to capital X in bracket, you can write it like this. Now it is sometimes better to reason in terms of these periodic extensions when dealing with the discrete Fourier transform, specifically if xk is the discrete Fourier transform of xn, then the inverse of discrete Fourier transform of xk is this, what we have seen. Okay, the signals xn and x bar n, you can say, are identical over the interval of from 0 to n minus 1. Now the interval is being given, so these signals are identical for the interval 0 to n minus 1, but may differ outside this range. Okay, this range is defined, but outside this range these may can differ. Okay, so similar statement can be made for the regarding the transform. We have made this statement for simple signal xn signal, but for the transform also we can make the same statement, that xk it may differ outside this range, means 0 to n minus 1. Okay, we can say that xk, sorry, capital X must be there, capital xk should be equals to or you can say that identical to x k bar, okay, for the over the interval of 0 to n minus 1, but may differ outside this range. Okay, So this is the basic about the discrete Fourier transform. Now the circular shifting and circular convolution we need to discuss. We'll discuss on the next lecture. Thank you. Thanks a lot.